So in this class, our major part is to focus on the three-phase induction motors as we have our AC machines. We actually managed to work with the AC machines, the first part, as you're working with the synchronous machines. So in this case, we are working with the induction motors, but under what? Three-phase. So as you have got your three-phase, know the connections that you are given under a three-phase. So operations of three-phase induction motors, I want you to go through those theory part, operations, and these definitions, this and that, so that we do not waste much time as we are having our exams soon and there's a lot of things to be covered. So guys, we're just gonna focus much on our calculations, what is important to be used in your exams. So, like I said, we simply have the part of our three-phase, and as we do understand, our three-phase is going to affect in the operation of connections being in delta or being in star. So that part we are used to it, guys. The voltages. In this case, if you are referring to the line voltage as the square root of 3 of what? The phase currents being the same. But actually, you'll be focusing on the voltages in the case of our calculations, as if the current is needed, but the voltages, remember in delta, these two are simply the same. So we are going to see with our calculations later on how to apply that part of our three-phase consideration. So as we have our induction motors, guys, just like what we considered before, as you're working with motors, you had the speed, the synchronous speed. We still have the same thing in our condition. As we are working with our induction motors, we have the synchronous speed. So in our calculations, it will be important that you do know how to calculate the synchronous speed and what is affecting that. So actually, let's focus on this one, guys. Like I said, the theory part is for me, guys. I'm just going to skip it. We'll focus with it when working with questions. That'll be important. That'll be important, guys, because of time. Time is not on our side. It's not on our side. Exams are just like few. It's now we are now talking about days, guys. All right, depending with when you're gonna watch this video. All right. So calculating the synchronous speed of an induction motor. So our synchronous speed will be referred as NS, just like before. So guys, this one, the formula hasn't changed. We still has the same formula that we used before, remember? 60 times F, which is our frequency, over what? The pair pose. And once we have got our 60 there, we said this must be in what? In revs per minute. So nothing has changed, guys. We still have our frequency. So there, still have our frequency. We still have what? Our pair pose, number of what? Pair pose. And that's our synchronous speed. So the synchronous speed and the actual speed will be used in the calculation of the slip. All right. So that will lead us to the calculating of the slip. Calculating slip. So in this case, we just gonna consider our slip as the relative speed. All right. So the slip is the relative speed of a three-phase induction motor, which is the difference between the synchronous speed and the magnetic, which is the synchronous speed, sorry, of the magnetic field. Remember, the part of the synchronous speed is of the magnetic field. So it is the difference that we're going to have between the synchronous speed of the magnetic field and the actual speed of the motor. So the difference gives us now a ratio which is going to be calculated as a percentage, or it can be calculated as per unit slip. All right. So as per unit slip. So slip is just gonna use letter S, right? So S per unit slip. Remember our ratio, NS, our synchronous speed minus N, which is our actual speed. So we're gonna use N to represent the actual speed. All right, the actual, this will be our actual speed. So remember, guys, if you're given the speed must be same units, revs per minute, all must be in revs per minute. All right, so the actual speed in our answering of questions can be referred also as the rotor speed. It can be, so that part can be, we can use any part that is representing that actual speed as per question. So we are going to see this part having an effect depending with your question, because it is the actual speed. So it's going to depend with the condition of that question. So we are going to talk about this N, all right? But the NS, the synchronous speed, guys, there is no way that we're going to talk about this to say it's going to be what? It's going to be back there. It'll be affected by the frequency and the purpose. Those are the two things, these two, which can affect our synchronous speed. All right? So the actual speed now, to be on a condition, so we're going to see like what exactly is it in our calculations, and this is per unit. So as a percentage, how are we going to calculate our percentage slip? We just have to multiply this part that we had by what? By 100%. So that will be our condition. So this is now percentage slip. So meaning to say, guys, in order for us to get rid of the percentage, we are simply dividing by 100, guys. We now know the concept of per unit from our transformers. We're dealing with per unit values, still one and the same thing. So this is what we have in terms of the slip. And we are going to consider also our slip are being affected. We are supposed to consider this part of our slip being affected on a condition where we have got, let's say these two guys are simply the same, because we're having a difference here. Let's say we are saying NS minus N over NS. And these two, they are equal. NS is equal to N. What is going to happen if they are equal? Meaning to say, if you are to subtract here on the numerator here, you're going to obtain what? You're going to obtain a 0. So whatever percentage of slip that you're going to have will be what? Will be a 0. Remember, guys, 0 over any number. 0 over any number. It can be over 2, it can be anything. It will give us what? A 0. So meaning to say, if the two speeds that we have are equivalent, are equal, our percentage slip will be 0, because they will be having a 0 there. So if NS is equal to N, all right, so let's start, okay, let's just call it this one 1. If NS is equal to N, therefore our percentage slip is equal to what? Is equal to 0. We are not going to have that value. It will be 0. So a 0 slip as a percentage or as a per unit slip, which is just 0. Remember, guys, it's just to remove percentage, you divide by what percentage? 100%. So it will be just 0. So if per unit slip is 0, it means the two speeds were simply equal. Another condition that also is important in your calculations of the slip is when you are given the condition of the motor that we are having when it is starting at a point of starting. All right. So at starting, it is important that we consider our percentage slip will be what? 100%. At starting, why is it that at starting, our percentage slip is 100%? It is because when you are starting the actual speed, you're starting, guys. So the motor, the rotor, there we are not talking about, it's not rotating. So there's no speed. We just have the synchronous speed of the armature, the part of the armature, the magnetic field. So we just have that. So any of that of the rotor there is zero there. So meaning to say it's going to be ns minus 0 over what? Over ns times 100%. So what are we going to have? Ns minus 0, it means ns over ns. This will cancel, which will give us 1. So 1 times 100% is what? 100%. So this is the condition of what? Starting, where our n is equal to 0. In this case, n is equal to 0. Once you, at starting, this is the moment where you are starting. You don't just start with a certain speed. You start at 0. These are the conditions that the rotor is at what? At standstill. That's at what? At standstill. Can be considered to be at standstill when the rotor is at what? At standstill. So here the rotor is at what? Standstill. In that condition, your percentage slip will be 100%. So as per unit slip, it will be what? 1. 100 over 100. Remember how to remove percentage. So it's going to give us 1. So whenever in exam, you are given a percentage slip of 100, know that the conditions are at starting, or they can give you to calculate something that is at starting. You must consider these conditions that are at starting, or when the rotor is at what? At standstill. These two are very, very important in terms of your sleep, because it's not always that you'll be given direct things. You just have to consider what is it that you have there. All right, then also, guys, as we consider our induction motors, it is important that we do understand how power is being lost due to the losses that we have up to the output. So this is best described using the energy flow. So it's another part, which is, this part is very, very important in answering of your questions. When you answer questions, follow the energy flow. So you've got the energy flow in a 3-phase induction motor. All right, in a 3-phase induction motor. It is very, very important, like I'm saying, this part, as we have the losses that will affect the induction motor. Remember that when you consider, or as you work with energy, guys, energy cannot be destroyed. Energy cannot, but it can be converted. It will be converted. It cannot be created. It cannot be destroyed, but it will be converted from one form to another. But in the form of our induction motor now, we are going to be having losses throughout. We'll be having losses up to the condition where we have the output power. As we have the stator, in the stator, there are losses. In the rotor, there are losses. There are also losses in part of the bearings. All these losses, guys, they represent part of what? Power. So it's power being lost. So which losses exactly are we going to consider in our energy flow? So remember, we've got part of the variable losses, which is your copper losses. Talked about these losses before. So nothing has changed, guys. Your copper losses, remember, that's I squared times R, which is our variable losses. Right, so this is part of what? Your variable losses. Okay, so if you also have got the iron, so the copper, where am I having the S? This is copper losses, or you can just have it in short like this. All right, so we've got the copper losses, then we've got the iron losses also in your calculation. So the iron losses, remember, these occur in the what? In the iron parts of the motor. Where we've got part of the eddy current losses and the hysteresis losses. Those, they do consist up to build up, they build up the ion losses. So we have got what? The eddy current. Guys, these ones we talked about them before, but let me write eddy current losses, and we also consider the hysteresis here. That's the hysteresis losses. So these are the ones that we'll be having, which occur in the ion parts. So these two, they build up the ion losses, guys. It's just building up ion losses, all right? Just like the copper losses, we are just considering to say they are referred as electrical losses, variable losses due to resistance. These are losses due to resistance. So it's the power due to resistance. As we have the electrical windings, remember. So that is the part now that you just need to consider. Where are we having the losses and how to have these losses? That is the condition. Then, as part of our bearings, as we have the bearings, from there we are going to have friction and windage losses. So we also have friction and windage losses. So all these losses, guys, is not like the first time that we are referring to, but just for you to know what you are exactly going to be dealing with. So the power, as it enters, as we start with the input to our induction motor, our three-phase induction motor, it will be affected with the stator. The first part that we meet is what? The stator. So as we have our stator, this is the first part that we are having. This is the first part that we have. So even in your presentation, the stator, you are going to use the subscript 1 to represent stator calculations. Like when we have got something around the stator, because this is the first part. So you indicate with what? With 1. So like I'm saying, the power is entering here. This is the input. So it enters, right? This is the first part that we are having. So it means exactly the input power is the power that is on the stator there. The input power here is the one that is on the stator. Please understand this part. It's very, very important. But the stator as we have it, it consists or it has the losses that are inside of it, which are iron loss. So you have the iron loss. We also have what? The copper loss. This is the losses that we are going to be having in part of the stator. These are what? Stator losses. So you can say stator iron plus copper loss. It's just one thing. Stator like this. All right. So what do we have as part of the stator? We've got the stator ion plus copper loss. These are the combined part in our stator. These are the losses that we are going to be having. And due to these losses that we have, it means the output that we have here, this is the most, here, especially here, this is the most important part. The output that we are having of what? The stator, this is the stator output. It is now affected here. Our stator output. It is now affected due to the losses that we have. A loss, guys, it means we are subtracting, we are removing, we are subtracting. We are subtracting whenever there's a loss. So meaning to say, as we are moving from this input power going there, we are going to be subtracting the losses. We have to subtract the losses to remove. The input power is always bigger than what we are going to have at the output. So in this sense alone here, in this sense alone, we are saying the stator output. It's a power. It's actually the power that we're talking about. but it's from the stator. So you can conclude that the stator output will be equal to what? Will be equal to what we started with, input, the input power minus the stator losses. That will be the condition. The stator losses, which is what? Iron and copper losses combined. Those are the stator losses that we have, guys. Input minus this. Stator losses that we have, iron and what? And copper. This is the one that we are saying as an output power as it is, just like the input here, it was entering what? The stator. So this output power that we are seeing, it is going to enter another section, which is what? Our rotor. Guys, we are referring to an output which was from another part of our machine, the stator. It is the output, yes, but it is entering somewhere. It is now entering what? The rotor. We are now entering the rotor, the second part. Just like we had one, so we're going to denote calculations which are on the rotor with the subscript 2. In terms of our calculations, we're just going to use the subscript 2. We're going to explain that one later on. So inside the rotor, just like what we had, when I have those losses, guys, just like what we have, our iron and what? And copper loss. These are the rotor losses. But I want us to focus here about this one because they try to give you confusion here about this power that is our output to the stator. And it also enters what? And it also enters the rotor. Just like what we have here, it is the input to the what? The input to the stator. So the output that we have from the stator is now the input to where? To the rotor this time. The same output that we are talking about is the input to the what? Is the input to the rotor here. So you can just call it rotor input in short. The same, this one, it is the same thing, this part. We are talking about the same thing here, this one. It is the same thing. What we had as our output, meaning to say this part here, what we had as our stator output must be also equal to what? To the rotor input. It is just one and the same thing. So that's our rotor input. So don't be confused when you're answering questions. They give you the rotor input. When they give you the rotor input, they're giving you what? The stator output. When they give you the stator output, what are they giving you? They're giving you the rotor input. It is the same point. We are at the same point. It is only you who is to define where are you from. If you are from the stator, you say this is the stator output. If you are entering the rotor, now you're entering the rotor, you're saying rotor input. Depends with how that information is given in terms of the questions. So just like what we had in our previous case, these losses that we have in the rotor, they will give us what? They will affect the output at the end. Whatever that is going to come out here, which is our rotor output. Here we now have the rotor output. Whatever that is going to come out is affected due to these losses. It is affected because of those losses that we have. It is affected. It is affected at the end. So starting from this point, remember, this is where we are. We're here. We are here at the stator output. We are still going this side. We are what? Subtracting. So meaning to say we can conclude on this part to say the rotor output, in this case, the rotor output, which is also called the gross output. They can give you this one as the gross output. They can give you this as the power developed by the what? By the rotor. All right? the power developed by the rotor. Still one and the same thing. So that rotor output can be given just like what we had from, we are moving from here. Remember, this is where we are. This is the stage where we left. We left where? At the stator output. Meaning to say we left where? At the rotor input, because we are saying the stator output and the rotor input are what? The same. So it is going to be rotor input. What is entering the rotor minus the losses that are inside the rotor. So you're going to subtract the rotor losses, which is the copper and the iron together. So this iron, this part here, yeah, the rotor input is where you left there. This is your stator output. You're simply having the same thing here. This is our stator output, remember. The rotor losses, which include of what? Iron and copper. So this is what we have, which is the one that we refer to as the output of the rotor output or the gross output. You can have it from that formula. So as we are moving out from the rotor, we can be affected by the bearings. In this consideration, we can be affected by what? The bearings. All right. So here, we can be affected by the bearings, which is the one that has got the friction. And windage loss is the one that I was talking about before here. Remember, we talked of the friction. All right, so we talked of the friction and windage losses. So these will be the ones that will be like the last part of our losses. After we have our rotor, we are affected by these bearings, which carries these losses to give us now the exact output. Take note between the rotor output. This is not our net output. This is just a gross output, something that we have before. There are still other losses to be considered. So meaning to say, as we are going to be moving from this part, subtracting the losses, just like what we are going to be having the exact output there. So this is where we have our P out, which is our output power. This is where we have what? Our output power, the net output. That is the consideration. So meaning to say, what has affected us to have this output are these losses here. So just like the previous case, we can consider now to calculate that output power from where we are here. It definitely means the output power, which is our net output, can be calculated. So P out, which is our output power, the net power there, we're now talking about the net power that we have, can be given. Remember, we are subtracting from where we left. Where we left is where? On the rotor output. Remember, we left here on the rotor output. So the rotor output that we have in that case, we're going to say the rotor output minus the losses that we have after. Remember, we're going this side. We were subtracting these losses. So we're going to subtract the losses encountered in the bearings, which is our friction and what? And windage losses. So you're going to subtract those losses. Just like that. We have our output. We have our output there. So this is the idea. So as a vice versa, here I was showing you from where? From the input. We started from the input. We are subtracting these losses. So as a vice versa, if you are given information, because information depends with how it is given from questions. As a vice versa from exam, if they give you information from the output going this side, what are you going to do? You are going to be adding the losses. So you must be very, very careful. So we can conclude that in actual sense, in this case, we must note that these two compared input and output, the input is actually greater than output. It's actually bigger than the output power. So in that case, from input, subtract losses. Subtract losses. As you move from the input going this side, you'll be removing losses. But from the output, you must be adding the losses now. So from P out, you add losses. So this is what you use in answering of your questions. With this information, you can answer a lot of questions in exam. A lot of questions have been cycling here. Understand this part. So like I said, in your denotions of the stator, in our calculations, we are going to be using the subscript 1. This is the first part that we have. Second part, the rotor. So at standstill, we are going to be remember the rotor, guys, that's where we are starting. So at standstill, going to be using the subscript 2. All right, stator 1, as we just have the flow chart 1, 2. And so that is how we're going to have it. All right, so this is it, guys. This is it. I don't know if we are together there. We just need to focus on the information, like I said, guys, that is important when you're answering questions. This information is important, very, very important. All right, so we're going to move on, guys. Like I said, you're going to need the calculations. So let us just quickly write what is important that we are going to need in our calculations. So you're going to consider the three-phase induction motor calculations. All right, so okay, now I think never thought it was gonna be this long, but anyways, let's try to finish because we'll need this information. In our next classes, I'm just gonna be talking about doing the calculations. So make sure that you go through all the classes, join membership so that you do not miss any of the classes that we shall have, because we shall be talking of examples as we move on. So in our calculations, guys, there is nothing much. We're gonna talk of the stator. So the first part is on the stator calculations, which are done in the stator. Like I said, guys, from our previous case there on top, we saw that the stator is the first part. So we're gonna represent with what? With the 1. So as you are working with the stator, I said you're gonna be using what? Subscript 1. So use subscript 1 in your presentation. Like let's say whenever you see the 1, know that they are giving you values or calculations about the stator. All right, so in our stator, the calculations that will be important, remember, we talked about the issue of being three-phase. So definitely will be affected on the voltages in star and in delta. Those are the ones that we can maybe talk about. Star connection, in a star connection, remember that the line voltage is equal to what? Square root of 3 of the phase voltage. So in our case, we are talking about what? The stator using the subscript 1. So it means we're going to just call it 1 and 1 here. So therefore, what can we say? Because as we are using 3-phase, remember our golden rule of the 3-phase. We use what? Phase values. Even under 3-phase induction motors, we are still under 3-phase. The golden rule is still the same. You use what? 3-phase, the phase values in your calculations. So meaning to say, therefore, as a phase value, what are you going to have? It is going to be the line voltage over what? over the square root of 3. So the 1, guys, 1 is simply denoting you are in the stator. You are in the what? In the stator. So as for delta, remember for a delta, these two are the same. So the line is equivalent to the what? To the phase. So 1, like I said, you're in the what? You're in the stator. All right. Also, they're going to ask you about the copper losses. All right. The copper loss, remember, copper loss, like I said, I squared times R, current times resistance. But what are we talking about here? A 3-phase. So you're going to multiply phase values times 3. So the copper loss will be 3 times I squared times R. These are phase values in what? In a stator. So you're going to call this P1, P1. Phase values in the stator 1, the stator. That's for a stator. All right. Also, for the stator, it is important that we do know that the impedance, which is the stator phase impedance, the stator phase impedance, remember impedance R plus JX. So in this case, we are talking about what? The stator. So the phase value 1, but the stator 1 there, 1. So it's going to be RP1 plus JR. All right. So we're now at X here. So this is XP1. So this is what we're just having. It's just addition of what we had before, guys. Nothing is new on these calculations. So that is what you're going to have. And also the current, if you're calculating the current, remember current voltage over impedance. So it's going to be the phase value over the impedance of the phase value. We're considering what? Phase values. So all these, guys, are stator because of what? The denotation of 1. They are stator values that we are talking about. They are stator values. But we are dealing with what? A 3-phase where the golden rule is what? Use phase values. That is why we are using what? This P, denotation of what? Phase values. These are phase values. So what I'm trying to say, guys, I'm not going to write all of these ones, but just like we are given IP1, just like IP1, what does it mean? What does it mean? We are simply talking of the stator, all right? The stator phase current. That is how you take it. Stator phase current. That's our stator phase current. All right? So given RP1, what does it mean? If you are given RP1, because those are some of things that you have there. Are we going to have stator phase resistance? That's still one and the same thing. Or the stator resistance per phase. What is important there? The stator. So this is our stator resistance per phase. Remember, we take per phase. These are phase values. Same with our impedance. Stator again. Stator what? Impedance per phase. That is what we have. Impedance per phase or phase impedance, the way that you want, guys. The way that you just understand it. Same with XP, the reactance. Stator again. It's all about the stator there. So it's the stator reactance per phase. Per phase. So guys, I'm not going to end all these. Just know that we are representing this part here to the 1, the 1, the 1. Then the P phase. These are phase values in our calculations. So as you consider the part of the stator, remember where we have the stator, that's where we have the stator output also. So this one, we already talked about it here. Here, remember, one part of the stator. So you're going to also add this one to say the stator output is this one. On those calculations about the stator, you add that one. I already talked about it, guys. So let's not waste time on that one. Let's move on to another part. So as we have from the stator, You go to the what? To the rotor. So the rotor, we said subscript 2 as we just follow up. 1, 2. So let's move on to the rotor, guys, and see what is happening in the rotor. So the rotor with a subscript 2. All right, so you're going to use the subscript 2 for the rotor, which is for rotor standstill values. For rotor standstill values. It is very, very important here. The part of the rotor, guys, here. Remember here. When we referred stator, it's 1. Rotor, it's what? Is 2. So as part of the rotor, what is important there, just for you to know this part. And also the rotor, remember, that is where we are going to be actually having, they can give us the connection also on the rotor, what is happening in terms of the power, three-phase connection, delta or what, or star. So we're not going to talk about much there, but they can give us the relationship between the turns and the voltage, just like we need to have the turns ratio. Remember, it can be used as a transformer, all right? Our induction motors can be used as transformers, remember? So the turns ratio, that's maybe the one that we can just focus on the turns ratio. So remember the turns ratio as we have, it's V1 over V2 is equal to what? N1 over N2. So in our case, we are like this, stator, rotor. So this is 1, this is 2. This is stator. This is what? This is our rotor. So as we consider 1, we are in the what? The stator. All right? And we are using phase values because these are three-phase calculation. Three-phase calculation, guys, you use what? You use phase values. You use what? Phase values. So the voltages are phase values. So we are going to have this as VP1 for what? The stator. I mean, the part of our stator. Over what? For the rotor now, because this is where, guys, we're talking of what? The EMF is being generated. The induced EMF. So we are going to be talking about what? The induced EMF, not just V2 as a terminal volt, but the induced EMF, the part of the rotor, guys. Remember, that is where now the rotation is starting. So we have what? The induced EMF. So we're going to take that one as the induced EMF. But remember, it's per what? Per phase. The 2 is representing what? Rotor. So it's stator to the rotor. So this is equal to the number of turns for the what? For the stator, the number of turns of what? Of the rotor. As what? Phase values. That is the condition. So the denotation of 1, do not forget 1, stator, 1. You're in the stator. 2, you're in the what? In the rotor. Do not forget. So that is what you're going to need on that part. I think also as I was writing this, I was explaining VP1 representing the stator phase voltage. Stator 1, stator. N1, stator turns per phase. As we talk about this EP2, you're now in the what? In the rotor. So this is the rotor induced EMF per phase. Stator turns per what? I mean, the rotor turns per phase. This one, yeah, 2. The rotor turns per phase. Just like that. So also, just like what we had previously, we had those resistances. Also, we have resistance which can be considered at standstill values. We also have what? We also have the resistance at what? Standstill. Resistance at standstill. And also we have what? Resistance at what? I mean, reactance at standstill. These are also part of what? Standstill values. That can be used in calculations as we're going to consider, just to know that maybe you'll be given what is important that you are in the rotor at standstill, they are giving you values. How you take your values, denote them as 2 so that, guys, we do not have confusion as we're going to be answering questions together. All right, then another part as we are considering this rotor is on the rotating rotor values. All right. We are simply having values which are inside the rotor, considering the rotor at standstill. This is the starting part that I was talking about. Remember, at standstill, when you're considering the part of what? The sleep, before we talked of the energy flow here. At starting, where the speed n there is 0, the actual speed is 0, the rotating speed, the rotor speed is 0. But now we are saying when rotating, no longer at what? At standstill. We are still the major part is we are still in the what? We are still in the rotor. But now we'll be considering rotating values when the rotor is now rotating. All right. So this time we're going to consider the subscript R for that, which are rotating. So this will be used for the rotating rotor values. So when there is a rotation that is happening, guys, we're going to use the what? The subscript R. That is how we're going to indicate our values. Meaning to say, we had the what? The induced EMF per phase in the what? In the rotor. But we no longer have that. We're going to have this as EPR, rotating rotor values. So how do we get to these rotating rotor values, which can be this one, which can be only reactance? We can be talking of that one, reactance. It can be of rotating rotor values, except for the resistance. How do we get these values? In order for us to get these values, we multiply our rotor values at standstill by sleep. Multiply two by what? By S. This is what I'm trying to say. Remember, 2, those are standstill values. So we are saying multiply standstill values by what? By sleep. If you multiply anything that is in standstill by sleep, you obtain what? The rotor rotating values. It is just like that part of, for those who are doing engineering science, when you're doing even those conversions of linear and angular motion, there were conversions. It is still one and the same thing. It is still the induced EMF per phase, but now at rotating values. It is still the same reactance, but at what? Rotating values. So those values, to get them, you multiply the what? The standstill values, 2 standstill values. Remember, 2 is for what? For standstill values. You multiply them by what? By the sleep. By doing so, you have the rotating rotor values. So e.g., let's consider for an example, this one. As we have our induced EMF per phase, our induced EMF per phase for the rotating values will be given as what? Remember we said standstill value times what? Sleep. So it's going to be sleep times the standstill value was what? Was given or was denoted by what? By 2. Remember, it was denoted by what? By 2. So this is the only case that is happening, guys. We're just taking the standstill values as we have them, we're just multiplying by what? By the sleep. But remember, as you were calculating the sleep before, the sleep, it was taken from what? The percentage sleep was taken from NS minus N over NS, where this NS has frequency inside of it. It has frequency. So as we consider the slip, it is also a product of what? Of frequency. It's a product of frequency. We have frequency inside of the slip. So anything that consider the frequency, remember frequency, voltages, I mean the EMF there, part of there, they'll be affected. Also reactances. So the reactance is going to be affected because we consider the slips or reactance of where the rotating values is equal to what? Slip times what? The reactance that we had of what? The standstill value. All right. It is only the resistance which is not affected because resistance is not affected by what? By frequency. So it follows that the resistance that we have as a rotating value, it is still the same resistance that we had as what? At standstill. It is still the same resistance that we had at what? At standstill. This one. So it therefore follows that, all right, this one, okay, it's important for you to just consider. So therefore, remember impedance, guys. So therefore, you can conclude that on number 4, you can calculate impedance, all right? So remember your impedance. How do you calculate impedance? Z is equal to R plus JX. So under rotating rotor values, our impedance per phase will be given as what? Under rotating rotor values, this one. R, our resistance, remember we said resistance of the rotating, guys, is same as what? Resistance at standstill. So we are going to take that resistance at standstill because this is the one that you'll be given because it's the same. This one is not affected. So you're going to take that one at standstill plus JX. Our reactance for these rotating rotor values, remember it's affected. This is our reactance here, which is what? X PR. For rotating rotor values, the reactance was what? Was affected. So you can even substitute, guys, here with its equivalent. What is its equivalent under what? Standstill values. This one, what is its equivalent? It's S, which is our slip times what? XP2. So you can even have it, our formula like this. It's one and the same thing, representing what? Our impedance per phase for the rotating values. Still one and the same thing. Manipulating this formula, guys, we can see it's one and the same. Nothing has changed there. We can even substitute direct like that. This is from our impedance. Remember, we're calculating current as what? Voltage over what? Over impedance. But in this case, our voltage is induced EMF. Remember, it's now rotating. So we're talking of what? The induced EMF there. All right. So let's also add there for current. So we can say current for the rotating values. Remember, we're under what? Rotating values is equal to what? Under rotating values, we use what? EP. That is under, as long as you're dealing with the rotor, guys, we work with what? Induced EMF. So, but here we are dealing with what? For the rotating values. So it's for the rotating values over the impedance for the rotating values, as we do understand division in polar form. So that's it. We have what? We have got this. So as long as you have this and this, guys, you're done. And also, the major part that we're supposed to first indicate here was supposed to be frequency, actually, because this is the major part that is affected. Slip times what? The frequency. This is the actual frequency, this one that we had, actual one that you're given from supply. From the what? From the supply, no problem. We have written that one. Then another part is on the what? The rotor copper loss. The rotor copper loss. So as we had before, remember the rotor copper loss, we had this before. So we're going to also consider the rotor copper loss 3 times what? I squared times R. So under the rotating values, our current, going to have our current. And like I said, the current is actually not affected, this one. All right. Sorry, the current is affected here. I said the resistance or current is now affected. This resistance here is not affected. Sorry for that. So meaning to say that is what you're going to have at the end in terms of your calculation. Remember, it's 3 phase. You're going to multiply by 3 and that. Yes, these calculations, we are going to need them. We are going to need these calculations. And as for the rotor output to this and that, guys, I'm not going to talk much about that because we've got our energy flow. Remember, I talked about that. So you add this here on the power. I want you to add this on your rotor. Remember, we talked about this, guys, to say for the rotor output, this is what you're going to have. And the net output, this is what you're going to have. You can also add those ones in terms of your calculations. And as part of your calculations, you must know that the power factor, guys, we are dealing with what? Induction motor. This is no longer to say about the rotor or what, the stator or what. For induction motors, guys, the power factor, we've got a lagging power factor. Remember, it's inductors, lagging power factor. So for power factor, in your calculations, you are going to be what? Having a lagging power factor. So for induction motors, major part there, inductors. All right, for induction motors, we have a lagging power factor. We have a lagging power factor. So this is the idea there, because in other calculations we saw, guys, you obtain a negative angle, but not to mean that it was because it was a lagging power factor. It was because of where the presentation of the quadrant, how the quadrant was presented. It is not about having a negative angle. A negative angle, guys, cos of a negative angle, I told you from your N5 that cos of a negative angle is a positive also. If it is an acute angle, remember, you'll be talking of an acute angle. So it will be a positive. Cos of a positive angle is also a positive. But for these ones, it's induction, as we are dealing with the induction, guys, from our industrial electronics N3 there. Where the what? A lagging power factor. So meaning to say, in your calculations, as you are dealing with what? 3-phase, we're going to talk of what? A lagging power factor. And also from current, the phase angle is taken what? From current. So we use phase angle from what? Use phase angle from what? From the current, which is our IPR for rotating values. The current that you'll be given, if you are dealing with rotating values, the current there, whatever, but that you'll be dealing with, the current is the one that you're going to use. The phase angle, remember, is definitely the phase value of current at a certain what? At a certain angle. That angle that you'll be checking there is the one that you're going to take as your phase angle. Then you consider to say the power factor is positive. All right. So remember your power factor. The angle there, as you calculate, you can consider it as positive, as negative. That one does not affect your calculations, guys. Your cos will remain as a positive value after that. But you're dealing with induction. You'll be having what? Lagging power factor at the end. So as you conclude that power factor, you must consider that it's what? It's a lagging power factor. So I want you to go through this information in as much as you can, guys. Answer questions with this information that I just gave you. Now you can answer as many questions as you can, and also to add other formulas that you're going to need. In this case, other formulas that we're gonna need. All right, gonna stop on this one. So just go through other formulas. All right, so using slip, you're gonna also need these formulas, and gonna try by all means to apply these. We consider our rotor input. All right, so the rotor input can be given from the rotor copper loss. All right, so it's simply rotor copper loss over slip. Also, you're gonna need the rotor input can also be calculated as rotor input into 1 minus slip. Also, we're gonna consider the rotor output here. This is output and also another rotor output, which is rotor copper loss. All right, I'm just going to rush here, guys, because of time. Then we'll see examples. As we move on, we're going to do examples. So make sure that you do go through the membership because we're going to have classes there working with examples and also question papers. All right. Then also we're going to talk of what the torque under our three-phase induction motors. How are we going to calculate our torque? So guys, we do understand our torque has not changed before from the output power. Remember, when you had the output power, you said it's 2nt over 60 like this. So we calculated torque from there by making what? It the subject of the formula. So 60p out over what? 2 pi n over 2 pi n is equal to what? To torque. So torque can be calculated that way. But in our case, we are considering the output the power there can differ. The output, the power that you're given can differ. They can give you as the rotor output. So you can use the rotor output over what? Over 2 pi n. All right. So that is our torque in what? Newton meters. Remember, torque is measured in what? Newton meters. Can take as the rotor output. Let's go back to our NH flow here. Rotor output here. Sorry, the rotor, yeah, this one, the rotor output. So the rotor output, it is because it is still having some other part to be removed as the losses before we get to the what? To the output. So we can also consider, remember, stator output is what? It's power also, which is what? Stator in, which is the rotor input. But it's output from somewhere. So you can also consider that rotor input. So they can give us the rotor input in our calculations. All right, for this torque, you can also consider 60 times rotor input over what? It's 2 pi n. All right, still in what? In Newton meters, like I said. All right, so this is what we are going to be having, or that we are going to be talking about, and go through conditions for maximum torque. We're going to talk about that in our next class or for other classes. Like I said, guys, make sure that you go through the membership, that you will get all the classes not affected by any class. You'll be having all classes, examples that we are going to be having using different sources that you can have question papers and also textbooks. So make sure that you go through the formulas that we listed in this class, then to go through examples where you still have a challenge in understanding of these. That is the purpose, guys, of the comment section. Let's communicate so that we can see how to apply the information. And for further calculations, membership is there for you guys. Till we meet again.